Okay, this is a third video on section 15.6 about triple integrals. And this is the last video on this section. And in this video, I'm going to work out a couple of problems on triple integrals. The first one is this. Let's think about this. Evaluate triple integral dv, meaning that the function you integrate is a constant function 1. The integrand is constant function 1. So that's why we omit 1. Integrate this where e is bounded by y is equal to x squared, x is equal to y squared, and z is equal to 0, z is equal to x plus y in the first octant. Okay, first of all, what is this? First octant. First octant means this positive part of the xyz space. Suppose you have xyz space, and of course it goes like this. And then this portion, where x is positive, y is positive, z is positive, this part is called first octant. Because xyz space is divided into 8 different regions. And the first region here is called the first octant. And then this part, the other part, so this part is called the second octant, and so on and so forth. And by the way, on the xy plane, this is called the first quadrant, right? First quadrant, second quadrant, third quadrant, and the fourth quadrant. And similarly, for xyz space, this part, everything is positive. That part is first, and the other side is second, and so on and so forth. So first octant, meaning that all of them, x, y, z, are positive. That's what first octant means. And now, for this problem, the region E, the solid E, is not given by the set notation. It's not given by a picture either. So you have to find it out, but it doesn't seem to be so easy to actually visualize what this E is. But yet, the point is that you could actually do this problem without even visualizing what E is. Like how? Well, like this. Let's remember one of the tricks I gave you last time about triple integral. So when you do triple integral, there are 3 variables, and you have to pick up one variable which you integrate, meaning that you fix the other 2 variables. And which one to integrate first? Well, basic rule of thumb is to pick up the variable which appears in the least complicated way. The least complicated guy is the guy you should take care of first. And then if you look at all those equations, y is equal to x squared, x is equal to y squared, and here we have x plus y. So x and y are quite complicated. On the other hand, if you look at just z just appears as z here, and it appears only twice. So apparently, if you look at all those expressions, the variable z is the least complicated variable. And that's a variable you should integrate first. Okay, so therefore integrate with z by fixing x and y. Okay, then since we are inside the first octant, x is always bigger than 0, and y is bigger than or equal to 0, and of course z is also bigger than or equal to 0. So therefore, if the boundaries of E, namely E is bounded by those 2 equations, z is equal to 0 and z is equal to x plus y, the smallest possible z is 0, and the largest possible z is x plus y for each fixed xy. right? Because all of them are non-negative, bigger than or equal to 0. So therefore, since this and this, we have a z between 0 and x plus y, and those are the limits for z. So therefore, the given integral is written as double integral, and you integrate with z, and z is from 0 to x plus y dz. And remember, the function we are integrating is 1, and we normally omit 1. And then we double integrate whatever we left with. And usually when you do a triple integral, you just leave this as d, and we figure this out later. And then we have d, and then z is, so if you integrate 1, you get z, and then z is from 0 to x plus y, and then dA, and this is double integral 0 x plus y dA. And then now we have to figure out what d is. Where d is. Then now, if you look at those equations, we are done with those. And then what we are left with is only those, y is equal to x squared and x is equal to y squared. So therefore, D is the region bounded by those two. What is that? Well, both of them are parabola, and indeed, x and y. And then this is y is equal to x squared, and x is equal to y squared is this parabola. And so therefore, this is the region you want to integrate. And then everything is symmetric between x and y, so it doesn't matter which variable you integrate first. So let's fix x, and let's integrate with y. And then y value is from here, but you have to solve this for y. Y is equal to root x. So y is from root x to x squared. So therefore, this integral here is x from x squared. I'm sorry, from root x. Wait a second. I said something wrong. The bottom line here, sorry, the curve here is y is equal to x squared. So you integrate from x squared to root x. Sorry about that. X squared to root x. And then x plus y. And then you integrate with dy. And then you move around x from 0 to 1 dx. And then this is equal to 0, 1. Then you integrate with y. Y is equal to x squared, and y is equal to root x dx. And then this is equal to 0, 1. And then x root x plus 1/2 x minus x cubed plus 1/2 x to the power 4. Okay, and then dx. It looks complicated, but I don't think there's any simpler way of doing this. And then if you just calculate this, you are supposed to get 3/10. Okay, so that's the answer. So the upshot is that for this problem, you don't really have to be able to visualize what this E is. However, can you actually guess how this E looks like? So the shadow of E on the xy plane is this, the region bounded by two parabolas. And then z is from 0 to x plus y, and z is equal to x plus y is just a plane. And indeed, the solid E looks like this. So this is just a side remark. E looks like this. Z-axis, and let me write down x-axis in this way, and then y-axis, and then the shadow of the solid is like a parabola, and then z is from 0 to a plane, so it looks like this actually, and then top portion here is z is equal to x plus y. That's how E looks like. So this is E. Anyhow, and then now also another note is this. So for this problem, we computed triple integral of a constant function 1. And then let me just summarize this. In general, not just for this problem, but in general, if you single integrate, if you look at the single integral of a single variable, and if you integrate 1 from a to b, and this is of course b minus a, and that's the length. Oops. This is the length of the interval line segment from a to b. Pictorially, you have the x-axis here, and you have a and b, and if you integrate the constant function 1 from a to b, what you get is just the length of this line segment. And then now, for double integral, if you double integrate the constant function 1 over some region D, what you get is the area of D. So pictorially, for double integral, you integrate over some region on the xy plane. This is D. And then finally, if you triple integrate constant function 1 over some solid E, what you get is the volume of E. And indeed, pictorially, it looks like this. This is our E. And then if you triple integrate the constant function 1 over a solid E, what you get is the volume of this solid. So therefore, for this problem, this number 3 over 10 is actually the volume of this solid. That's what we compute it. All right. Okay, let's do one more problem about triple integral. Here is the question. Let's consider this triple integral. F of x, y, z, dy, dz, dx. Okay, let's consider this. So f of x, y, z is just some given function. And of course, if you are just given a triple integral like this, and if you are given some explicit function, there's nothing to do, basically. You just integrate this portion, and then you integrate with z, and then finally you integrate with x, and you get the answer. But the question is now, this problem is this. Suppose you are given, given triple integral like this, and then visualize the solid E namely the region of integration, the solid of integration, namely the solid given by those limits, and integrate with z first. Okay, how are we going to do this? Here's the answer. First of all, since you already know the limit for each variable, you can actually write down the solid by using the set notation. It's a set of all xyz such that, well, y is between those. So y is between 0 and 4 minus 2x. So that's the first limit. And then next variable is z, and z is from 0 to a root 4 minus x squared. And then finally, the variable x is between 0 and 2. Okay, and then now, so therefore, what's a given integral? Given integral is, well, if you integrate with z first, you take care of this variable first. And then z is from 0 to root 4 minus x squared, and we have some integrand, and then dz. And then if you want to integrate, then, okay, that's when you integrate with z first. And then let's say if you want to integrate with y, you get this. And this. Okay, that's fine. Excuse me. But then now, we're going to visualize the solid. Well, can you visualize it? Well, look. Z is from 0 to root 4 minus x squared. And so z is 0. First of all, z is 0. Z is equal to 0 is the xy plane. Now, what's the other one? Well, this is, if you look at the boundary, this, and this is actually written as z squared plus x squared is equal to 4. And if you look at this on the xz plane, if you look at the xz plane, this is just a circle with radius 2. But we have to look at it in the xyz space, and on the xyz space, this is a cylinder parallel to the y-axis. And indeed, yeah, it looks like this. Y. And then, so this one basically appears a circle with radius 2, on the xz space, xz plane. But we are looking at only a in the first octant actually. This is 4 minus. And then z is from 0 to the cylinder. The cylinder like this. Cylinder like this. Okay. And this surface is z is equal to, the part of this cylinder is like this. But then now, at the same time, your y is between 0 and 4 minus 2x. What is that? Well, on the xy plane, y is equal to 4 minus 2x. It's just a line with slope negative 2, y-intercept 4. And in fact, it goes through this point and that point. This line here is y is equal to 4 minus 2x on the xy plane. But on the xyz space, it's a plane parallel to the z-axis. No z appears here, so that means it's independent of z. That means it's parallel to the z-axis. So therefore, what you have to do is to cut this cylinder by the plane defined by this. So therefore, actually it turns out that the solid of integration, let me move it a little bit. Looks like this. And then like this. This is our E. So this top surface here is z is equal to root 4 minus x, sorry. What am I doing? Okay, this is x, sorry. This is x squared, sorry. This is z is equal to root 4 minus x squared. And then this is the plane defined by y is equal to 4 minus 2x. Okay, then now that's fine. That's essentially the answer. But then now, so far so good. But what if this? The question number 2 is this. Let's integrate with x first. So in principle, if you have a triple integral, in principle, it doesn't matter which variable you pick up first. Although in practice, often the time y is easier than the others. But now, question is this. Integrate with x first by fixing y and z. Then what's going to happen? By the way, it's not a good idea, but it's just an exercise, just a question. Well, for this, so we fix y and z. That means you fix some point on the yz plane. So that yz plane is here, somewhere here. You fix some point on the yz plane. And then you vary x. So that means x starts from 0. Okay, x always starts from 0. That's fine. But then now, if you go up in the direction of x-axis, you hit this plane if your fixed yz is here. But if you are fixed yz somewhere around here, and if you move in the direction of x-axis, what you hit is this surface, z is equal to root 4 minus x squared. So therefore, you have to separate the integral into 2 different pieces, depending on where you are on the yz plane. And it turns out that in this case, so let me just copy this. So if you look at the shadow of this picture on the yz plane, namely if you project this down, everything on the yz plane, what you see is something like this. And then you have a rectangle. This is 4. And then you have a curve like this. And then here, by the way, if you solve this for x, you get x is equal to 2 minus 1/2 y. And if you solve this for x, you get x is equal to root 4 minus z, solve for x, z squared. Because you are now integrate with x first, you have to solve everything for x. And then, like I said, if you are in this region here, R1, let's call this part R1. If you are on R1, for each fixed y and z, your x is from 0 to this, root 4 minus z squared. And then whatever the integrand is. And then dx. And then you double integrate whatever you are left with over the shadow of the solid. But as long as you are on this R1 region, the shadow is R1. Oops. Shadow is R1. Plus, now, if you are on this portion, R2, in this case, your x is from 0 to this plane. So x is from 0 to 2 minus 1/2 y dx. And then you have to double integrate whatever you are left with over the shadow. But in this case, the shadow is this portion, R2. You have double integrate over R2. Okay, so that's the integral you have to set up. So you have to separate into two different regions. And then, by the way, what's this curve here? The curve is the intersection of those two. Intersection of this guy and this guy. So by equating those, you will see that this is z is equal to root 4 minus 1/2 y squared. Okay, so what I did is to plug in this x to, well, you can actually equate those two, or you can just plug this into here. Okay. Anyhow, so that's the that's pretty much it. So in practice, of course, it's not a good idea, but this is a little fun exercise to see if you are understanding the basic idea of triple integrals. Okay, so that's all for this section.